In this video, we are going to learn the divergence theorem. Now, this theorem gives us a simpler way to compute flux through a closed surface. So jumping right into the statement of the theorem, let S be a piecewise smooth closed surface that encloses the solid region E with outward orientation. So it is important that our surface is closed. So think of the surface of a sphere. That would be a great example. And then the sphere that it encloses, the solid sphere, is the region E. Outward orientation is going to be defined as the positive orientation of the surface. So if we want inward or negative orientation, then we're going to have to adjust the statement of the theorem. Then let f of x, y, z be a vector field whose component functions have continuous partial derivatives on an open region that contains E. If all of this is true, then the divergence theorem states that the double integral over S of f dot ds is equal to the triple integral over E of the divergence of f dv. So we've equated a double integral, which is the surface integral of a vector field, to a triple integral, which is the triple integral of the divergence of that vector field. Now mathematically, why this works, divergence is a derivative, or can be thought of as a derivative of the vector field f. We are integrating divergence, so we're taking the integral of a derivative. The fundamental theorem of calculus then comes into play. The integral of a derivative just gives the original function, which in this case is the vector field f. So we'd be left with the double integral of the vector field, which turns into the surface integral on the left-hand side. Now in terms of flux, what is this theorem saying? So on the left side, we have the flux of the vector field across the boundary surface of E, which is S. And on the right side, we have the triple integral of the divergence of the vector field over the solid region E. So on the left side, we're computing the flow of the vector field across the boundary surface of the solid region. And then on the right side, we're computing the divergence at all of the interior points of that solid region. And what that should give us is really just how much of the vector field is moving across the boundary. And we'll see why on the next slide. The positively oriented closed boundary surface S can also be written in terms of E with that partial notation. And that really emphasizes the fact that the surface is the boundary of the solid region, and those two ideas are connected. The same way we made the argument for Stokes' theorem when we were expressing the boundary curve in terms of the surface. Now the divergence theorem also has two other names it could be referred to as, which are Gauss's theorem or Ostrogadzki's theorem. And depending on the resource you're looking at, you might see these other names for the divergence theorem. But we're going to call it the divergence theorem in this video. So taking an informal look at why the divergence theorem works, if we recall that the divergence of a vector field measures how much the field acts like a source, positive divergence, or a sink, negative divergence, near a given point. So essentially, computing the divergence at every point tells us if it's creating field or taking away field. So then when we look at the divergence theorem, that states that if you sum up all these infinitesimally small sources and sinks within the region E, so all of the points inside of that solid region, so that's the interior points, but also the points on the surface of the region, because it includes all of those points, it's equivalent to finding the flux of the vector field across the boundary surface S, or the flow through that boundary surface. Now, going a little bit deeper, essentially the divergence is telling us how much field is created or taken away at each of the interior points. And if we sum all of that up, basically we're going to see a bunch of cancellation happen in the interior or with the interior points until you get to the points on the boundary of that solid region. And then, as we look at how much field is created or taken away, as it moves out of that solid region, there's nothing to cancel with. So really, that's the only divergence that actually winds up counting in a way. And then, well, looking at how much field goes through a boundary surface, that's flux. So that's why we get the equivalence that we do with the divergence theorem. It's really just an idea of conservation. What's created or taken away inside of the solid region has to be equivalent to what's moving in or out through the boundary surface. Now, if the region E has a boundary surface S with inward orientation, then the adjustment to the theorem, double integral over S of f dot ds, then is equal to the negation of the triple integral over E of the divergence of f dv. So a simple adjustment, if we have inward or negative orientation, we're just going to negate the triple integral that we're evaluating. Now, divergence theorem works in both directions. We could use the double integral of the vector field, so a flux integral, to compute the triple integral of divergence. It's less common. We're going to stick in this video moving in the right direction. So in this case, going from a flux integral to the triple integral of the divergence of the vector field we're given. So use the divergence theorem to evaluate the double integral of f dot ds, where the vector field is x cubed, y cubed, z cubed, and S is the positively oriented boundary of the solid region enclosed by the sphere x squared plus y squared plus z squared equals 4. Okay, so first thing I like to do is draw out the region just to make sure that it is closed. Now here we have a sphere, so we don't have to go through the process for this particular example, but I think it's a good habit to get in. So if we draw our sphere of radius 2, that is a closed surface, so we can apply the divergence theorem as they indicate, which is a good sign. Then we're going to take the divergence of the vector field f. That's going to be 3x squared plus 3y squared plus 3z squared. So by the divergence theorem, that double integral, that flux integral we're asked to compute is equal to the triple integral of 3x squared plus 3y squared plus 3z squared dv over the region E, which in this case is the sphere. In order to evaluate the triple integral over a spherical region, spherical coordinates are going to make the most sense. So next step is to convert this to spherical coordinates. So we have the triple integral. 3x squared plus 3y squared plus 3z squared converts to 3 rho squared. dv becomes rho squared sine phi, d rho d theta d phi. And now we need to determine our bounds. So that is where our picture can be helpful. So rho goes from 0 to 2, that's the radius of the sphere. Theta goes from 0 to 2 pi. And phi goes from 0 to pi. And just as a reminder, phi bounds are always between 0 and pi, and then we adjust based on the other surfaces, right? So if it's a cone, maybe it's 0 to pi over 4, but we should never go outside of 0 to pi for our phi bounds. Now, our focus in this video is on the divergence, so we're going to focus on setting up. I will give you the answer for each of the triple integrals we set up, but I leave the actual integration for you to practice. So here, you would get 384 pi over 5. And the divergence we left positive because we had positive orientation or outward orientation, right? Just to visualize what that means is that means the normal vectors were pointing outward from the sphere. Okay, our next example, use the divergence theorem again to evaluate the double integral of f dot ds, where the vector field is x squared yz, and S is the boundary of the tetrahedron bounded by the coordinate planes and the plane 2x plus y plus z equals 2 with outward orientation. So again, let's draw the region. So we have x, y, and z. So the x-intercept is going to be 1, the y-intercept is going to be 2, and the z-intercept is going to be 2 as well. So there's the portion of the plane in the first octant, which is all we care about since we also are bounded by the coordinate planes. So in blue, I'm just going to go over the solid region that we're looking at. So we have the plane, and then we have the 3 coordinate planes. So there is our tetrahedron, and that's the region E that we're integrating over. Next, we need the divergence of the vector field. So the divergence of F is equal to 2x plus 1 plus 1, which is 2x plus 2. So that flux integral we are asked to compute, since it's a closed surface, we can set up a triple integral of divergence, so 2x plus 2 over the region E dv. Now for this particular region, I think it makes the most sense to stay in the Cartesian coordinate system, so x's, y's, and z's. So that means we need to set up our bounds. So triple integral of 2x plus 2. So we'll go dz first. So the plane is 2x plus y plus z equals 2. So solving for z, we get 2 minus 2x minus y. And then it's also bound by the xy plane, which is z equals 0. So we're going from 0 to 2 minus 2x minus y. Then we can take a look on the xy plane to see what our bounds in terms of x's and y's are going to be. So we can just transfer the intercepts 1 and 2. So we have a triangular region there. This would be y equals 2 minus 2x. We can do this as a type 1 or type 2 region in the xy plane. I think type 1 makes things simple, but honestly they both work nicely. So that means we're going dy dx for our order of integration. Y goes from 0 to 2 minus 2x. X goes from 0 to 1. And if we were to integrate that out, we would get a value of 5/3. Okay, so make sure we have a closed region. We did. Find the divergence, set up the triple integral, and evaluate. And again, outward orientation, we didn't have to do anything with our triple integral. Next, find the flux of the vector field, which is e to the y, y minus x e to the z, e to the x, across the surface S, which is the boundary of the solid bounded by the cylinder, x squared plus y squared equals 9, and the planes z equals 0 and y plus z equals 4, oriented inward toward its axes of symmetry. Okay, so just highlighting here, we do now have inward orientation, so we're going to have to negate our triple integral. Next, let's draw our surface, or our surfaces, to see the region that we're bounding. So we have a cylinder of radius 3. So cylinder of radius 3. Then we have z equals 0, which is the xy plane. So we have the bottom of that cylinder. And then y plus z equals 4. So z-intercept of 4, y-intercept of 4. So the plane is going to look like this. We sketch it out. So in blue, let's look at the intersection of the plane and the cylinder. So it's going to be this diagonal. So we have a truncated cylinder here. So it cuts the cylinder on a diagonal. Then we have the cylinder, and we have the xz plane. So there is our solid region E that we're integrating over. It is closed, so we can use the divergence theorem. Now, if we weren't using the divergence theorem, because they didn't tell us to here, what that would mean is we would have to compute 3 separate flux integrals. The flux through the cylinder, which is the side, the flux through the disk at the bottom on the xy plane, or z equals 0, and the flux through that diagonal surface, which is formed by the plane and the cylinder, right, the intersection of the two. We'd go through the process of each, so let's just run it through the cylinder. For the cylinder, we'd have to parameterize the cylinder, so that would be 3 cos theta, 3 sine theta, z. We'd find the partial with respect to theta, partial with respect to z, find the cross product. That's going to define the normal vector to the surface of the cylinder. You have to make sure that points in the right direction, which is inward. Then you redefine the vector field in terms of theta and z. You dot it with the normal vector, and then you evaluate that double integral you get to find the flux through the cylinder. And that's just one of the 3 surfaces. So our motivation to use the divergence theorem here is the fact that it's going to be much simpler, and we only have to evaluate 1 triple integral as opposed to 3 separate flux integrals. So just to make a note, they're not always going to tell you to use the divergence theorem, like they do not here. But we need to pick up on the situation that happens when it would make sense. So in this case, a closed surface, it makes sense to use the divergence theorem. So now, using the divergence theorem, so the flux That's what we were looking for. We're now going to set up that triple integral. Now, inward orientation means we want to negate our triple integral, so we'll just get that negative in there so we don't forget about it later. Then we're going to find the divergence of the vector field. So that's going to be 0 plus 1 plus 0, which is equal to 1. So we have the negation of the triple integral of 1 dv over the region E. So that really just means that we are finding the volume of this region. Now, because one of the surfaces is a cylinder, cylindrical coordinates are going to make the most sense here. So we're going to go r dz dr d theta. So z goes from 0, which is the z equals 0 plane or the xy plane, up to the plane, which is y plus z equals 4. So solving for z, we get 4 minus y, but we have to convert this surface to cylindrical coordinates. So that means we have z equals 4 minus r sine theta. So z goes to 4 minus r sine theta. And then we can draw the region on the xy plane to figure out our r and theta bounds. So we have a circle of radius 3 as the region we'd be integrating on the xy plane. So converting that to r's and thetas, that means r goes from 0 to 3, theta goes from 0 to 2 pi. If we evaluate out this triple integral in cylindrical coordinates, we're going to get negative 36 pi. So this example brought a few new pieces in. First, inward orientation, so we had to negate our triple integral. Second, they did not tell us to use the divergence theorem, so we had to talk about why it would make sense to use the divergence theorem in an example like this. Our last example, evaluate the double integral of f dot ds, so that flux integral, where the vector field is yz xz x squared, and s is the paraboloid z equals x squared plus y squared, where z is bound from 0 to 1 with outward orientation. Okay, so if we start by drawing our surface, x, y, and z, we have a paraboloid like this. Okay, so that's our surface S. Outward orientation, so that means our normal vectors are going to point downward there. Now this is not a closed surface, right? So S is not closed. Since S is not closed, we don't have the setup for the divergence theorem, right? It only works if we are finding the flux through a closed surface. So what could we do? We could either do this directly, which is find the normal vector of the surface. In this case, we can use the gradient of a function g, because we could use a trivial parameterization, and then we would go and redefine the vector field. So we'd want to replace z's with x squared plus y squared, dot it with the normal vector that we find, and set up the double integral. That is definitely an option. But looking at the x squared and y squareds that we would get, it seems that that might be a little bit complicated. Maybe if we add in an extra surface to create a closed region, that would give us a simpler way to compute this flux integral. So that's what we're going to do here. So we're going to create a situation where the divergence theorem can be used. So what we need to do is add in the plane, which we'll call S1, and that's going to create a closed region. So now our closed region, so I'll use green now since I already used blue for the normal vectors. So our closed region is the paraboloid and that disk on top. So that's our region E. Outward orientation, so that surface or that disk, we'd want that normal vector to point straight up. And that will be important in a moment. Okay, so what we have here now is a situation where the flux integral we were asked for, plus the flux through the surface that we added in, that can now be equated to the triple integral over the region E of the divergence of f dv. Okay, so now by summing up these two flux integrals, we create a closed surface. So then we can use the divergence theorem. So what this means for actually solving the problem, we're going to do the divergence theorem, but then we have to compute the flux through S1 directly, so with that procedure that we talked about earlier, and then subtract the value from the value we get using the divergence theorem. Okay, so we have a plan, now let's actually execute it. So first, let's do the divergence theorem. Or we'll just say divergence. Keep it simple. Okay, so first up, divergence of the vector field is going to be 0 plus 0 plus 0. So that means that we are evaluating the triple integral over that region E that we have defined in green of 0 dV, which is just 0. So this is a really nice example where if we get the divergence to be 0, then the triple integral of 0 is 0, and we don't have any integration to do at all. Next, we need to evaluate the flux through S1, so through that plane. Okay, so flux through S1. Okay, so that's really that double integral over S1 of f dot ds. Okay, so the surface is z equals 1. So what we're going to do is create a function g of x, y, z, which is equal to z minus 1. Gradient of g is equal to 0, 0, 1. So we need to make sure that this vector is pointing in the right direction, so it orients the surface correctly for us to maintain outward orientation through that closed region. So that's where that blue vector I drew through the plane is important. So it points straight up, as does our gradient vector. All right, so right there, straight up, so we're good. Then we're going to dot this with the vector field, so f dotted with the gradient of g. That's going to just give us x squared. Okay, so now we have the double integral, or I'll set it up right here, double integral of x squared dA over some region D, but the region that we're integrating over is going to be a circle of radius 1. Because if we think about the intersection, right, we have the intersection of z equals 1 and z equals x squared plus y squared would just be x squared plus y squared equals 1. Right? So that's giving us the region. So this is going to make the most sense to evaluate in polar. So let's go to another slide to evaluate this. So we have the double integral. X squared is going to be r cos theta squared. dA becomes r dr d theta since we're going to polar. We had a circle of radius 1 set up, so 0 to 1, 0 to 2 pi. Okay, so we can separate this. So integral from 0 to 2 pi of cosine squared theta d theta times the integral from 0 to 1 of r cubed dr. This one I'll actually integrate through since we have a cos squared. It's good practice for us. So this is going to be the integral from 0 to 2 pi of 1/2 plus cos 2 theta over 2 d theta using that double angle identity times the integral from 0 to 1 of r cubed dr. So we get theta over 2 plus 2 theta would be your u, du would be 2. So we make our adjustments there. So plus sine 2 theta over 4. Evaluate that from 0 to 2 pi. And then we get 1/4 r to the 4th, and we evaluate that from 0 to 1. So we're going to get pi times 1/4, which is pi over 4. Okay, so now going back to that first equation we wrote, we have the flux integral that we were originally asked to find, plus the flux that we just found through the surface we added in, S1, and that's equal to the triple integral of the divergence of the vector field, which was 0. So solving this for the flux integral we were looking for, that means the flux through the paraboloid of the given vector field is negative pi over 4. So this is an example where we did not have a situation where we could use the divergence theorem. We added an additional surface in to create a closed surface. We can use the divergence theorem then in that case, but then we had to compute the flux directly through the surface that we added in. Very similar to problems that we looked at with Green's theorem, where we didn't have a closed curve for the line integral. We closed it, used Green's theorem, but then took away the line integral of the part we added in. So we set up triple integrals in Cartesian, x, y, z's, in cylindrical, and in spherical. So we hit all three of those to review those ideas. We talked about the divergence theorem and a couple of cases where we could use the divergence theorem even if they did not tell us to. So practice with this, make sure you feel comfortable, but this theorem is really helpful for finding flux through closed surfaces.